So let's consider that you have the following cylindrical conductor, which is connected by wires to a power source. So it's connected by electrical wire to the following power source. In that case, the moment you turn on that power source, in addition to having an electrical current flowing through that conductor, you also have a certain potential difference or a certain voltage which is going to be applied to that conductor. Now, depending on the electrical behavior of that conductor, meaning depending on how the voltage and the electrical current would vary through that conductor, we can distinguish two types of electrical devices. So depending on the electrical behavior of that conductor, we can distinguish two types of electrical devices. We can distinguish the ohmic devices and we can distinguish the non-ohmic devices. So we can distinguish two types of electrical devices, which are the ohmic devices, and we can distinguish the non-ohmic devices. So like I said, depending on how the voltage and the current would vary through that conductor, therefore we can distinguish two different types of electrical devices, the ohmic and the non-ohmic ones. But how can we distinguish between them? How can we distinguish between the ohmic devices and the non-ohmic devices? Starting with the ohmic devices. A device is said to be ohmic if it obeys Ohm's law for all voltages applied, meaning that if the amount of current flowing through that device is actually proportional to the amount of voltage applied. So whenever you vary the amount of voltage applied, the amount of current flowing through that device is going to vary in a proportional manner to the voltage. And therefore, for an ohmic device, the graphical representation of the variation between the voltage and the current is actually a straight line relationship. So graphically, the relationship between the voltage and the current for an ohmic device is actually a straight line relationship. And mathematically, the relationship between the voltage and the current for an ohmic device is given by Ohm's law to be V equal to the current times R, where R in that case would be none other but the resistance. So as we can see over here, R is actually a positive proportionality constant. Let's say proportionality constant between the voltage and the current. So for an ohmic device, we can notice over here that the slope of that straight line is actually none other but the resistance. Moreover, we can distinguish over here that since we have a straight line, therefore the slope of that straight line is a constant from start until finish. It's constant throughout that entire straight line. That implies that the resistance for an ohmic device is also a constant. So it doesn't matter how many times you vary the voltage for an ohmic device, the electrical current is going to vary in a proportional manner in such a way to keep that value of R always a constant. So for an ohmic device, we always have a constant resistance. So over here, for an ohmic device, we have a constant resistance, and we label that resistance as a static resistance. Now moving on to the case of the non-ohmic devices. Now in the case of the non-ohmic devices, the resistance is no longer a constant. So that proportionality between the voltage and the current is actually lost in that case. So for a non-ohmic device, now graphically the relationship between the voltage and the current is not going to be a linear one, but rather it's going to have the following curvy shape. So as we can see over here, now we don't have any linearity anymore between the voltage and the current, which is an indication that the voltage and the current are not varying in a proportional manner to each other as before. And moreover, the slope of that curve that we have over here is no longer a constant. The slope, which actually represents the resistance, is no longer a constant in the case of a non-ohmic device. So for a non-ohmic device over here, we don't have a constant resistance, but rather a varying one, and therefore we label that resistance as a dynamic resistance. So for a non-ohmic device, whenever you vary the amount of voltage applied, the corresponding amount of resistance is going to vary as well. And therefore we don't have a static resistance anymore, but rather we have a dynamic resistance. So to recap, in the case of the ohmic devices, the voltage and the current, they are proportional to each other. They are varying in a proportional manner to each other. Whenever the voltage varies, the corresponding current varies as well in a proportional manner. Moreover, graphically, the relationship between them, it's a linear relationship. Therefore, the slope of that linear relationship, which is none other but the resistance, indicates that the resistance is always a constant for an ohmic device. So no matter how many times you vary the voltage, the resistance is going to remain a constant for an ohmic device. Whereas for a non-ohmic device, now the resistance is going to vary with every voltage applied. And therefore, graphically, the relationship between the voltage and the current is no longer a straight line, but rather it has a curvy shape, which is an indication that the voltage and the current are no longer preserving that proportionality between them, and moreover, the resistance is no longer a constant for a non-ohmic device. Now, among the many non-ohmic devices, we can actually distinguish the following light bulb with a tungsten filament inside. So as we can see in that figure, inside the light bulb we have a tungsten filament. A tungsten filament is basically a metal filament. It's a conductor. So in that case, when you have an electrical current applied to that tungsten filament, the temperature of that tungsten filament is going to increment from room temperature to the actual operating temperature, or to the maximum operating temperature at which the filament would be constantly glowing. So when the temperature of that filament starts to increase from room temperature and it goes up, therefore the intensity or the amount of light which is given off by that light bulb is going to vary as well until we reach the maximum operating temperature of that filament, for which that light bulb would be given off a constant light. However, that increase in temperature from room temperature to the maximum operating temperature is actually associated by an increase in resistance within that tungsten filament. So the resistance of the tungsten filament is actually increasing with every increase in temperature. But what would be the relationship in that case between the resistance and the temperature? How can the resistance be affected by the temperature in that case? Let's consider the following battery resistor circuit. The resistor is basically, it's a piece of conducting material that has a particular resistance. So any conducting material, it has its own internal resistance. So we can label that conducting material as a resistor. Moreover, that resistor or that conducting material over here, it consists of atoms that make up the solid structure of that resistor. So inside that conductor over here, we have multiple atoms that make up the solid structure of that resistor. And as long as that resistor is maintained at room temperature, therefore these atoms are going to have their own natural vibration, meaning that they are going to be vibrating around equilibrium position but at a very minimal amplitude. So over here, each atom is going to be vibrating up and down. It's going to have a very minimal amplitude of vibrations, and as long as the temperature of that resistor is actually maintained at room temperature, therefore these atoms are going to maintain a certain equilibrium position of vibration, meaning that they are going to be vibrating in a very limited manner around that equilibrium position, and therefore the vibration of these atoms is actually very natural to them. It is basically called the lattice vibration. So the atoms of any type of material, they basically have their own natural vibration, which we call it to be the lattice vibration. And as long as you maintain that material at room temperature, therefore these atoms would be maintaining a certain equilibrium position of vibrations. Now what would happen if we actually turn on that power source? So let's move on to the following simulation. So as we can see in that battery resistor circuit, if we look above at that conductor, which is basically a resistor, we can see that we have green spheres. These green spheres, they basically correspond to the atoms that make up the solid structure of that conductor. So as I have said before, when the conductor is actually maintained at room temperature, therefore these atoms are going to have their own natural vibration, meaning that they are going to be vibrating about an equilibrium position. And these vibrations, they aren't like they don't have a very high amplitude, but rather they are very minimal vibrations. Now initially the battery is turned off, so we are not supplying the conductor with any electrons. Now what would happen if we actually increase the amount of voltage applied? So over here, let's say we started from 0 volts and we start to increment the amount of voltage applied. So as we can see, what's happening is the battery is supplying that conductor with an electrical current, and we know that the electrical current is basically the flow of electrons. So the electrical current that goes out from the negative terminal circles around and then enter into the positive terminal. So as we can see over here, we have the flow of electrons coming out of the negative terminal, and the electrons in that case, they are indicated by these blue spheres. So in that case, the moment you turn on the battery and you have a flow of electrons going out from the negative terminal, these electrons, upon their entrance over here into that conductor, they are going to collide with the atoms of that resistor. So as we can see over here, upon entrance and throughout that entire conductor, the electrons are entering into collisions with the atoms that make up the solid structure of that conductor. However, each electron is basically carrying an energy, and more specifically, it's carrying an electrical energy. Therefore, upon collision between each electron and the atoms of that conductor, therefore, the electron is going to lose part of its energy. It's going to give off part of its energy to these atoms. Or in other words, it's going to give off part of its energy to that entire conductor. Therefore, the temperature of that conductor is going to increase, because that energy which is being lost by the electron is going to be lost in terms of heat, and that heat is going to be absorbed by the atoms of that conductor. Therefore, the temperature of that conductor is going to increase. Now, moreover, that increase in temperature is actually going to lead to an increase of the average kinetic energy of each atom. So now, as we can see, when we initially started at 0, the atoms were barely moving. And then, as we started to increment the voltage applied, now we are seeing much more rapid vibrations and at a higher amplitude for the atom, which is an indication that the amount of energy which is being lost by the electrons and being absorbed by that conductor is actually being absorbed, or it's being supplied to the atoms in terms of kinetic energy. So now each atom is going to be gaining speed. So it's going to be vibrating at a much higher amplitude and more rapidly. So what would happen if we keep increasing the voltage in that case? So as we can see now, first off, we are supplying more and more electrons to that conductor, but however, now the atoms of that conductor, they are vibrating more rapidly and at a bigger amplitude. Therefore, these atoms are intercepting the passage of the electrons furthermore whenever they gain more speed. So whenever they start to vibrate more rapidly, therefore, they are able to intercept the passage of more and more electrons. So if we keep incrementing the voltage over here, as we can see, first off, the temperature below, the temperature of that conductor is actually increasing. So the temperature over here of that conductor is actually increasing with every increase in voltage. And moreover, these atoms now, they are vibrating more rapidly and at a bigger amplitude, so they are intercepting the passage of the electrons furthermore. So if we reach the maximum voltage over here, as we can see now, the temperature of that conductor, it increased drastically. And moreover, now over here, the atoms of that conductor, they are vibrating at a much greater amplitude and in a very rapid manner. Therefore, they are intercepting the passage of the electrons furthermore, which is basically an indication of what? So if you are intercepting the passage of the electrical current furthermore, that implies that you are hindering or you are impeding the passage of the electrons. Therefore, what you are actually doing is you are increasing the resistance of that conductor. So as we can see over here, an increment in temperature, it was accompanied by an increment in resistance, and that increment in resistance, it happened through the fact that the atoms of that conductor, since they have gained kinetic energy, they were able to oscillate at a much higher amplitude and in a more frequent manner. Therefore, they were able to frequently intercept the passage of the electron, which is none other but the passage of the electrical current, and therefore incrementing the resistance of that conductor. So to wrap it up, so initially over here we started at 0 volts, where the atoms had their own natural vibrations, as we can see, and the initial temperature of that conductor, it was at room temperature. Then after we started incrementing the voltage, now we were supplying that conductor with electrons, with an electrical current. So upon entrance of these electrons into that conductor, they entered into collisions with the atoms of that conductor. However, since the electrons are carrying electrical energy, so upon each collision, these electrons are going to lose part of their energy, and that energy in that case is going to be absorbed by that conductor. In other words, it's going to be absorbed by the atoms. However, that energy which is lost by the electrical current or by the electrons is actually lost in terms of heat. And moreover, that absorbed heat, it started to lead to an increase of the temperature of that conductor over here. So the more we incremented the voltage, as we can see, the greater the temperature it became. But in addition, that increase in temperature of that entire conductor, it led to an increase of the average kinetic energy of each atom, meaning that each atom it gained speed. So the atoms of that conductor, now they started to oscillate, as we can see, at a greater amplitude and more frequently. So these frequent collisions, they are going to lead to an increment in the amount of collision. So these frequent oscillations are going to lead to an increase in the amount of collisions between these atoms and the electrons. So if we have more collisions now between the atoms and the electrons, that implies that the atoms are impeding the passage of the electrical current. So they are basically incrementing the resistance of that entire conductor. So if we keep on incrementing the voltage applied, as we can see, the corresponding temperature of that conductor is incrementing as well, and moreover, the oscillations of these atoms are also incrementing. They are becoming more frequently and oscillating at a much higher amplitude, and therefore intercepting the passage of the electrons furthermore, which is going to lead to an increment in resistance of that conductor. And hence the direct relationship between the temperature of that conductor and the amount of resistance of that conductor. So far we have seen in the case of a non-ohmic device the dependence of resistance on temperature. So whenever the temperature incremented, the corresponding amount of resistance of that conductor incremented as well. Now in the case of some conductors that have a very specific geometrical shape, the resistance in that case is not going to be solely dependent on the collisions between the moving charges and the atoms of that conductor. In other words, it's not going to be dependent on the temperature as we have just seen before. But in that case, the resistance of such conductor is going to be dependent on geometrical and chemical parameters. So for example, it's going to be dependent on the length of that conductor, on the cross-sectional area of that conductor, and on the resistivity of that conductor. Starting with the length of a conductor. How can the length in that case affect the resistance of a conductor? Let's consider that we have the following two cylindrical conductors. So we have the first conductor, which has a certain length L and a certain cross-sectional area A. And then we have a second conductor, which has 2 times the length of the first conductor. So its entire length is actually 2L, but it has the same cross-sectional area A. So in that case, how can the length affect the resistance of a conductor? So we are going to suppose that both conductors are being traversed by the same electrical current I. In that case, when you make the conductor or the wire lengthier or longer, therefore what you are basically doing is you are prolonging the path of obstacles that the electrons have to overcome. So we have seen in the previous case that when the electrons enter into that conductor, they are going to enter into collisions with the atoms of that conductor. And therefore, the more frequent these collisions are, the greater the resistance is going to be. Therefore, when you prolong the length of that conductor, what you are basically doing is you are extending the path of obstacles that the electrons of that electrical current have to overcome to get from that point to that point over here. Therefore, you are basically incrementing the resistance of that conductor. So in that case, the resistance is directly proportional to the length of a conductor. So whenever you use a lengthier conductor, therefore you are extending the path of obstacles that the electrons have to overcome in order to get through that entire conductor, and therefore you are incrementing the resistance of that conductor. So the resistance and the length, they are directly proportional to each other. Now, how can the cross-sectional area affect the resistance? So let's consider the following example. Now, where we have that first rod of a certain cross-sectional area A and a certain length L, and then we have a second cylindrical rod of the same length L. So that second rod, it has the same length as the first rod. However, now the cross-sectional area A prime of the second rod is equal to 3 times that initial cross-sectional area. So over here we have 3 times greater cross-sectional area than the first rod. So in that case, how can the cross-sectional area affect the resistance of that conductor? The greater or the larger the diameter of a cylinder is, therefore the more current or more charges can flow through that cylinder, which is going to have a counter effect on the resistance of that conductor. So let's say over here we have an electrical current I flowing through the first conductor, and in the second conductor we also have the same current I flowing through it. In that case, the greater or the larger the diameter of a conductor is, therefore more electrons are going to be allowed to flow through that conductor. So for example, let's say over here that first conductor is allowing 100 electrons per second to enter or to flow through that conductor, whereas that second conductor, which has 3 times the diameter of the first one or 3 times the area of the first one, let's say it's going to allow on average or at least 300 electrons per second to flow into it. So that incremental number of charges is going to have a counter effect on the resistance of that conductor. So basically it's going to decrease it. Therefore the resistance is basically proportional to the inverse of the area. Therefore whenever you increment the area of a conductor, therefore its resistance is going to decrease. You can make the analogy to water pipes. So if you have 2 different water pipes of 2 different diameters, let's say the one which has a smaller diameter is going to allow a much smaller volume of water to flow into it, whereas the one with the greater diameter is going to allow a greater volume of water, a greater quantity of water to flow into it. So therefore the drift of water is going to be greater in the pipe which has a greater diameter, and the same thing for the electrons over here. So the one with the greater diameter or the one with the greater cross-sectional area is going to allow more electrons to flow into it, which is going to have a counter effect on the resistance of that conductor. Therefore the resistance is proportional to the inverse of that cross-sectional area. Now moving on to resistivity. So what's a resistivity? The resistivity, it depends on the material used, meaning it varies from one material to another. So basically it's an intrinsic property of a material. So the copper rod, it has its own resistivity, the aluminum has its own resistivity, steel has its own resistivity, etc. And the resistivity in that case is defined as the ability of an object to provide impedance or to provide resistance. So the resistivity basically, it gives rise to resistance. So the greater the resistivity is, the greater the resistance is going to be. In addition, resistivity, besides depending on the nature of that material, it also depends on the atomic structure of that material. So if you have a material with very random atomic structure inside of it, therefore the resistivity is going to be greater, because in that case you're going to have much more collisions between the atoms of that material and the electrons. Whereas if you have a material which has a very organized atomic structure, for example like the copper rod, therefore that organized atomic structure is going to lead to a decrease in resistivity. That's why conductors like the copper rods, like the aluminum rods, they have very low resistivity because they have a very ordered atomic structure which actually decreases their resistivity. And as we know, the resistivity is basically the main function or the main property in order to have resistance. So the lesser the resistivity is, therefore the smaller the resistance is going to be. So in that case, we can deduce that the resistance of a material is directly proportional to its resistivity. So the resistivity is denoted by rho. So any material with a greater resistivity, that implies that that material it has a greater resistance. So these two parameters are directly proportional to each other. So far we have proven the dependence of resistance on chemical and geometrical properties. So for example, over here the resistance is directly proportional to length. Over here the resistance is inversely proportional to area, and over here the resistance depends on the chemical property of a material, which is represented by that resistivity. So by combining the dependence of resistance on the chemical and the geometrical parameters of a conductor, we can basically establish the following relationship, that the resistance is equal to rho times the length over the area. So as we can see over here, the resistance is inversely proportional to the area, meaning that the greater the area is, the lesser the resistance is going to be. Moreover, that resistance is directly proportional to rho, which is the resistivity. So the greater the resistivity is, the greater R is going to be. And R is also proportional to the length. Therefore, the lengthier a conductor is, in that case you are extending the path of obstacles that the electrons have to overcome. Therefore, this is going to lead to an increment in that resistance. So we have that final expression for a conductor of a very specific geometrical shape, which is given as R equal to rho times L over A. So let's consider over here the following simulation, which is studying the dependence of resistance on the resistivity from one side, on the length, and on the area from the other side. So down below over here we have a cylindrical conducting material, and inside of that material, as we can see, we have indicated the atoms with black dots. So all of these black dots, they represent the atoms distribution within that material. Now what would happen if we increment the amount of resistivity of that material? So as we have seen before, the resistivity is directly proportional to resistance. So whenever you are incrementing the resistivity, as we can see over here, we are basically incrementing the amount of atoms that make up the solid structure of that material. So whenever you are incrementing the amount of atoms, that implies that now you have much more collisions between the electrons and between the atoms of that material. The higher the number of collisions is, therefore the greater the resistance is going to be. So R and rho, they are directly proportional to each other. And if we lower the resistivity, so as we can see, we are basically lowering the random distribution of atoms within that material. Therefore, we are lowering the amount of collisions between the electrons and between the atoms of that material. Now regarding the length, as we have seen before, whenever you increment the length of a conductor, basically you are prolonging the path of obstacles that the electrical current has to overcome in order to go from one end to another. So as we can see, whenever we are incrementing the length, we are basically over here creating more obstacles for the electrons to overcome. So on each side now we have much more atoms, or much more random distribution of atoms that the electrons have to overcome in order to go from one end to another, and therefore R is directly proportional to the length. Whenever you increment the length, therefore you are basically incrementing that resistance. Now what would happen if we vary with the area? So initially we are starting at an area of 7.5 centimeters squared. So when we start to increment that area, as we can see now, the diameter of that cylinder is becoming greater. So we are not affecting the length, we are not varying with the length, and we are not varying with the resistivity, but rather we are varying over here with the area, with that cross-sectional area. So as we can see, whenever you are incrementing the cross-sectional area, that implies that you are allowing a bigger number of charges, a larger number of charges to flow into that conductor, which is going to have a negative effect or a counter effect on the resistance. Therefore, you are incrementing the probability of electrons to go from one end to another in comparison to when you had a smaller diameter over here at 7.5 centimeters squared. So the greater the diameter is, therefore more charges per second are going to be allowed to enter through that conductor, which is going to have a counter effect on resistance by decreasing it. So the area and the resistance are inversely proportional to each other. And that would be it regarding our topic of the day.